October of the year 2025 stands as a moment without precedent in the chronicles of astronomy. Two entirely separate celestial bodies are rushing toward the sun at the same time, yet from utterly different points of origin. The interstellar traveler known as 3I Atlas arrives bearing a chemical fingerprint so strange it defies the conventional rules of how stars and their fragments are born. In contrast, the comet SWAN R2 has erupted in brightness with such astonishing speed that it hints at a substance utterly unlike anything catalogued from our familiar Oort cloud. Together, their convergence forms what could be called a cosmic traffic jam, an alignment that statistical models predict should only occur once every few million years. And yet, astonishingly, they are both set to meet the sun less than 28 days apart. Mission Control tracks their paths, as if drawn by the hand of geometry itself, each trajectory folding inward with mechanical exactness. Meanwhile, instruments pick up chemical irregularities that undermine decades of accepted cometary science. Then comes the most unsettling twist. As both voyages slip into the furnace of solar brilliance, our telescopes will be rendered blind during the very window when the greatest revelations might unfold. And so the question hangs in the air. Is this overlapping timing merely chance, or is there something or someone ensuring that our gaze is turned away? Stay with me, for October of 2025 may prove to overturn everything we thought we understood about what truly moves in the dark between the stars. Two strangers have slipped into our solar system, one slender and swift, cloaked in a ghostly green shimmer, the other expansive and radiant, unfurling a luminous tail that sprawls across swathes of sky. They were born in distant corners of the cosmos, yet here they are, arriving together at our sun in a kind of celestial duet that forces astronomers to double-check every equation. The first revealed itself on the 1st of July, 2025, captured in the digital gaze of the Atlas Survey telescope in Chile. At first, it was no more than a solitary pixel, a flicker of light that did not belong. Hours later, calculations betrayed the truth. This object, christened 3I Atlas, followed a hyperbolic path, unbound by the gravity of our Sunday. Another interstellar voyager, the third ever confirmed to cross the boundary of our solar dominion. The second newcomer surfaced only months later, rising from the glare of dawn as if conjured from the ether. Designated Comet C 2025 R2, it was first spotted in SWAN imagery on the 11th of September. Already dazzling enough for binoculars, already trailing a magnificent plume praised by backyard stargazers, it now occupied the relentless attention of NASA's Jet Propulsion Laboratory. In sterile control rooms, machines whispered constantly, telemetry flowing in steady rhythm, while radio dishes around the globe tracked these travelers with the metronomic precision of a heartbeat. Each stream of data told its story: luminosity curves, spectral fingerprints, orbital refinements, etched down to a tenth of an astronomical unit. Yet numbers, however exact, cannot capture the experience of the sky. Step outside on a crisp October night, away from the haze of city lights, and you may see them both. Through a modest telescope, 3I Atlas appears as a faint smear, its emerald hue subtle yet undeniable to those who know where to look. SWAN R2, by contrast, seizes the western horizon at dusk, its sweeping tail like a cosmic brushstroke across the canvas of twilight. Our instruments murmur in tongues beyond human hearing. The sharp tick of CCD shutters freezing photons that began their voyage millions of years ago. The soft hum of spectrographs splitting starlight into elemental code. Across continents, ground stations relay torrents of measurements, digital rivers streaming toward analysis centers where human minds wrestle with what the machines reveal. But the cosmos itself remains mute. Across the vacuum, no sound carries only light, only radiation, whispering truths in frequencies that hint these objects are not entirely what they seem. 3I Atlas cuts through space with a speed that feels purposeful, its path aimed at a rendezvous with the sun on the 29th of October, 2025. At 1.35 astronomical units from the star just inside the orbit of Mars, it will graze close enough to raise unsettling questions. SWAN R2 keeps its own timetable. It brushed past the Sun on the 12th of September, diving to within half an astronomical unit before turning outward, and its nearest brush with Earth will come on the 21st of October, passing only 0.27 astronomical units away, astronomically speaking, skimming our doorstep. The timing gnaws at astronomers, who sit long after midnight staring at monitors, uneasy at the improbability. Two wanderers, utterly unrelated, arriving in the same season. The mathematics insists it should be rare beyond reckoning. Yet here we are, witnesses to what may be the most extraordinary convergence ever recorded, or perhaps to something less accidental. The green glow of 3I Atlas has seized attention. Spectra reveal diatomic carbon and cyanogen, molecules that blaze emerald when struck by solar light. Such signatures are natural for comets awakening near the Sun, yet the steadiness and vividness of this coloration have unsettled specialists who have studied comets all their lives. SWAN R2 carries its own enigmas. Its explosive brightening after solar conjunction suggests a chemistry unlike the familiar denizens of our Oort cloud. Its tail grows in ways both recognizable and oddly divergent, as though following a score written in a dialect not entirely our own. And scale, always merciless in space, draws the starkest contrast. 3I Atlas, a slender spear of light, compact and directed with uncanny resolve. Current estimates suggest that the solid heart of 3I Atlas is only a few kilometers wide, a modest size by cometary standards, yet large enough to drive the restless activity astronomers have been tracking. SWAN R2, by contrast, unfurls across the heavens like a glowing shroud, its coma and sweeping tail stretching across whole degrees of sky when viewed from Earth. Now we enter October of 2025, the month when both of these visitors rush toward their closest rendezvous with the Sunday. On the 3rd of October, Mars itself claims a privileged vantage point. The red planet's orbit will carry it within 30 million kilometers of 3I Atlas, and there our robotic scouts, cameras, spectrometers, orbiters will aim their eyes at the interstellar intruder, gathering precious data that may finally chip away at the mounting riddles each new observation has raised. Yet October brings with it a severe complication. As the objects near their solar encounters, Earth's geometry betrays us. The glare of the Sun swallows them, forcing our ground-based telescopes into blindness during the most decisive stages of their journeys. For weeks, perhaps for months, we will lose them entirely, unable to follow their passage. When at last they emerge from behind the furnace of our star, if indeed they reappear, what tales will our instruments record? Will they return unchanged, marked only by the expected wounds of solar fire? Or will they carry evidence of something stranger, something that unsettles the very framework through which we interpret the traffic of the interstellar void? This is the question that shadows every clear night of October. Is what we are seeing merely a comet, or could it be a fortress, or even the long-delayed answer to a signal we never knew we had sent? The universe has set two enigmas in our skies, and October of 2025 may be the only chance to resolve them before they vanish again into the endless dark. But to grasp what their presence means, we must first understand not only how we found them, but perhaps more disturbingly, how they found us. The story of discovery rarely begins with a thunderclap of revelation. More often, it starts with the quiet patience of photons striking silicon detectors scattered across observatories worldwide. Each night, robotic telescopes sweep their assigned sectors of sky, electronic eyes collecting images destined for comparison, subtraction, and scrutiny by algorithms trained to notice what should not exist. The Atlas survey that revealed 3I Atlas operates 4 telescopes across 2 continents, each armed with wide-field cameras capable of watching enormous stretches of sky at once. On clear nights, they generate torrents of data, hundreds of gigabytes, millions of stars measured to exquisite precision. Out of this flood emerges the trace of an interstellar wanderer, a single point of light sliding too fast, drifting in the wrong direction. Yet Atlas is only one voice in a global choir of sleepless sentinels. The Catalina Sky Survey in Arizona, Linear in New Mexico, Neowise, orbiting high above Earth's atmosphere, all contribute to a network of instruments that never blink, never rest, forever alert to disturbances in the cosmic order. When SWAN R2 appeared in imagery from the Solar and Heliospheric Observatory, the first to notice was not a NASA professional, but an amateur. Vladimir Bezugli, poring over SWAN data for his own research, spotted the anomalous brightening that would soon become one of the great comets of 2025. This is the rhythm of modern astronomy. Professionals and amateurs, machines and human intuition, all converging to capture the brief, fragile moments when something new slips into our neighborhood of the stars. The detectors whisper in the language of photon counts and pixel intensities, but it takes human insight to hear when those whispers rise into a shout. Different instruments disclose different truths. Visible light cameras show us the shape, the glowing nucleus, the swelling coma, the tail that streams outward like a celestial weather vane pointing away from the Sunday. But to truly know what these bodies are, we must pry open their light and examine the colors hidden within. Spectroscopy turns starlight into story. Molecules in a comet's coma absorb and re-emit sunlight, stamping unique signatures onto the spectrum we receive. The Very Large Telescope's view of 3I Atlas revealed striking details: strong emission lines of cyanogen and, more surprisingly, nickel atoms glowing faintly in the vacuum of space. Nickel has appeared in comets before, but its intensity here caught attention. More troubling was what did not appear iron lines that almost always accompany nickel in natural samples. The imbalance carved a chemical fingerprint that slipped beyond our standard models of comet formation. The James Webb Space Telescope joined the chorus in August of 2025, its infrared eyes uncovering a nucleus dominated by carbon dioxide and curiously poor in water vapor, at least at the distances observed. Such a profile suggests a body whose outer shell holds volatile ices that ignite at low temperatures, sparking activity long before water ice contributes to the coma. SWAN imagery offered yet another perspective. Its ultraviolet maps of hydrogen, created as sunlight splits apart water molecules, provided a three-dimensional portrait of vapor expanding into space, revealing structures invisible to ordinary telescopes. Meanwhile, the Hubble Space Telescope delivered crisp images that constrained the size of 3I Atlas's nucleus. Likely a few kilometers across, substantial enough to account for its activity, yet small enough to have slipped unnoticed until it had already crossed deep into our solar system. Each observation adds a shard to a puzzle whose complexity only grows with each piece. Yet instruments can mislead as easily as they illuminate. Automated processing systems are designed to recognize the familiar to catalog, the predictable ballet of objects following Kepler's laws around the Sunday. And what happens when something arrives that refuses to conform? When something in the sky behaves differently, even in the smallest ways, those differences can be blurred by the very algorithms designed to impose order on the data. Take the challenge of measuring brightness. Comets do not brighten smoothly as they fall sunward. Their light curves are shaped by a tangle of processes: the sublimation of different ices at different distances, the spin of irregular nuclei that bring active patches into and out of sunlight, and the sudden release of dust and gas from vents that flare unpredictably. Disentangling natural variability from truly anomalous behavior demands the eye of experts who live within the subtleties of cometary physics. The emerald glow of 3I Atlas underscores this complexity. Several molecules can radiate green under cometary conditions. Diatomic carbon is the usual suspect, fluorescing when solar light strikes. Cyanogen, too, can add to the color. Without high-resolution spectra to pin down the exact culprit, the green haze remains a suggestion, not a conclusion. Media, however, thrives on suggestion. Reports of unfamiliar chemistry or unusual orbits can be amplified into extraordinary claims long before peer review tests the evidence. Science corrects itself, but often at a slower pace than public appetite for answers. Here, the instruments are vital, not just as detectors of the strange, but as anchors in a sea of speculation. Telescopes have no hunger for drama. They record photons, measure positions, and build archives of numbers that, in time, yield truth. Safety concerns sharpen the focus of these observations. Both 3I Atlas and SWAN R2 follow paths that spare our planet. 3I Atlas will pass no closer than 1.8 astronomical units, about 270 million kilometers. SWAN R2 approaches to 0.27 astronomical units, still 40 million kilometers away. Neither is a threat, but each offers a rare window into material born under alien conditions. Time, however, is the enemy. As October of 2025 wears on, both objects sink into the glare of the Sunday. Earth-based telescopes will soon be blinded just as the encounters grow most compelling. Space observatories have clearer views, but only for limited hours, and must divide their attention among countless cosmic priorities. What emerges is a portrait painted in light curves and spectral lines, orbital elements and chemical traces. But even portraits can deceive. What if the first to be misled are not the public, but the instruments themselves, or the people interpreting them? Still, the telescopes persist, patient as machines can be, harvesting photons and tracking paths with mechanical fidelity. Yet as our visitors descend toward the solar blaze, the instruments' voices grow fainter, and into that hush slips the oldest of questions. What secrets hide in the silence when the sky itself falls quiet? Deep space speaks in the language of atoms, and 3I Atlas is composing a tale in an unfamiliar accent. When the Very Large Telescope trained its powerful spectrographs on this interstellar guest, astronomers were startled by what they found. Nickel vapor glowed in the tenuous halo around the nucleus, yet the iron lines that should have accompanied it were absent. In spectroscopy, every element writes its name in light. Excited by solar radiation or collisions, atoms release photons at fixed wavelengths, fingerprints as distinct as DNA. Nickel imprints its mark in the green part of the spectrum, contributing to the ethereal tint that has made 3I Atlas a favorite among astrophotographers. But nickel is rarely a solitary traveler. In meteorites, in asteroids, even in comets where it has been glimpsed, nickel typically appears with iron, paired in proportions that trace their shared birth in stellar furnaces billions of years ago. By all cosmic logic, where nickel shines, iron should follow. Yet, 3I Atlas seems to have ignored that rule. During the comet's surge toward its August 2025 brightness peak, the VLT registered strong nickel lines that blazed against the background spectrum. But when it searched for iron, it found none upper limits so strict that, had iron been present in its usual abundance, it would have been obvious. The absence is puzzling, and theories abound. Perhaps nickel-rich organic compounds, stable in the deep freeze of interstellar space, break apart near the sun to release nickel atoms first. Or maybe eons of cosmic weathering have altered the surface chemistry in ways our models cannot yet capture. The universe, after all, is under no contract to match human expectations, nor is 3I Atlas the first interstellar visitor to carry chemical surprises. Comet 2I. Borisov revealed a carbon monoxide to water ratio far higher than comets born here, pointing to an origin in a frigid, carbon monoxide-rich disk around another star. Yet 3I Atlas stretches the anomalies further. Observations by the James Webb Space Telescope showed a nucleus dominated by carbon dioxide, with little water vapor at the large distances observed. Such layering suggests an onion-like structure, highly volatile ices like carbon dioxide sublimating early, water joining only as the comet draws nearer the Sunday. Cyanogen adds another twist, its emission lines flaring under ultraviolet light as organic molecules disintegrate, though their relative intensities deviate from the familiar patterns of homegrown comets. The green that has so enchanted the public thus remains enigmatic. Diatomic carbon is the usual explanation, but cyanogen, and even certain states of carbon itself, can also paint a comet emerald. Only ultra-high resolution spectroscopy could assign definitive blame. For now, the color remains a mystery wrapped in beauty. Taken together, these signatures weave a chemical story that resists easy classification. If atoms are letters and molecules are words, then 3I Atlas is writing in a dialect dominated by carbon dioxide, laced with metallic syllables that defy our grammar. The composition fits the broad possibilities of comet formation around alien suns, yet is strange enough to demand our attention. Gas production rates add to the portrait. As the comet closes in, molecules sublimate faster, their output rising with each reduction in distance, a behavior consistent with known physics. The mathematics of sublimation allow astronomers to forecast activity with confidence. And yet, anomalies intrude. The ratios of gases diverge from solar system norms, while the light curve flickers in ways that hint at uneven surface chemistry or bursts of hidden activity from beneath the crust. Within the predictable framework, the comet whispers variations, small deviations that remind us we are watching something born under foreign stars. The global community of amateur astronomers has become an essential partner in decoding these chemical riddles. From backyards and rooftops, high-quality images trace the shifting shapes of the coma and the evolving sweep of the tail as 3I Atlas drifts toward perihelion. This constant coverage fills a gap professional telescopes cannot, constrained as they are by scarce observing time and competing priorities. Social media magnifies these findings, sometimes too eagerly, transforming tentative anomalies into dramatic headlines that race ahead of the evidence. The report of nickel without iron, for example, has been spun in some corners into speculation about artificial design metallic structures engineered rather than accreted. Such claims stretch far beyond what the data can bear. NASA's official stance remains steady. To their scientists, the comet is a natural interstellar traveler, chemically unusual but not beyond the bounds of astrophysical expectation. Peculiarities are precisely what one would predict for bodies born around other suns, shaped in environments with different temperatures, pressures, and elemental balances. The European Space Agency, coordinating ground campaigns and space missions, echoes the conclusion. While its teams acknowledge the unusual chemistry, they point out that the essential physics of cometary behavior, ice is sublimating, gas expanding, dust streaming, provides a framework that explains the observations without invoking exotic alternatives. Still, anomalies are where science grows, and 3I Atlas offers more than enough to sustain research for years. The nickel glow, the carbon dioxide dominance, the cyanogen lines, the emerald haze, all are puzzle pieces that may illuminate not only this single wanderer, but also the processes of stellar system formation across the galaxy. As October of 2025 advances, chances to probe these mysteries are fading. The comet is sliding towards solar conjunction, its growing distance from Earth and shrinking elongation from the Sun conspiring to blind our ground-based instruments. We may not see it again until it re-emerges months later, if it re-emerges at all. If chemistry is a language, then this comet speaks in a dialect of ice and metal, one that carries echoes of birth conditions, perhaps hundreds of light years away. Whether that dialect is nothing more than a variant of familiar physics and chemistry, or whether it hints at something shaped with intent, is the unresolved riddle of our October sky. The atoms themselves do not deceive, but neither do they reveal all the truths we long to hear. Picture the solar system as a vast clockwork engine, its planets tracing patient ellipses around the central fire, while asteroids, comets, and the occasional interstellar wanderer weave through, guided only by the mathematics of gravity. Now imagine two strangers from space, arriving along utterly different paths, from utterly different directions, yet timing their closest approaches to the Sun within mere weeks of each other. The odds of such synchrony should be infinitesimal, and yet in October of 2025, that is precisely what we witness overhead. 3I Atlas first revealed itself in July, rising from the direction of Serpens Corda, discovered only when it became bright enough for automated surveys to catch its trace. Its orbit is unmistakably hyperbolic, the signature of an object unbound by the sun's pull. With an inclination of roughly 175 degrees, it moves retrograde, cutting against the current of planetary motion like a salmon forcing its way upstream beneath the ecliptic plane. SWAN R2 tells a different tale. A long-period comet born in the deep freeze of the Oort cloud, it had spent millennia in darkness until gravity nudged it inward. It emerged from the glare near Virgo, concealed for months by the sun's brilliance, until its orbit swung it wide enough to blaze into view. These geometries explain the nature of their discoveries. Interstellar objects like 3I Atlas can hide for long stretches, approaching from arbitrary directions, often lost in solar proximity until they are already among us. By the time Atlas's telescopes flagged it, the comet had crossed Jupiter's orbit and begun to show faint signs of activity. SWAN R2, meanwhile, was subject to the Holochek effect, a quirk that delays the recognition of long-period comets. They brighten near the sun, but while still too close to its glare to be seen from Earth, only when geometry shifts do they suddenly appear in twilight skies. That is exactly what happened in September of 2025, when SWAN R2 exploded into visibility. The result is a calendar that feels too precise to be coincidence. SWAN R2 reached perihelion on the 12th of September, diving to within half an astronomical unit of the Sunday. On the 3rd of October, 3I Atlas brushed close to Mars, sweeping within 30 million kilometers of the red planet. By the 21st of October, SWAN R2 will skim Earth at a distance of just 0.27 astronomical units, while 3I Atlas completes its own solar encounter near the 29th, approaching to 1.35 astronomical units. Within 6 weeks, the two objects check every milestone in their journeys, clustering together in a way that stretches the limits of chance. Probability suggests such alignments are rare beyond measure, yet in a universe filled with billions of comets and the occasional interstellar wanderer, even improbable dice rolls must eventually appear. The contrast between the two could not be sharper. 3I Atlas presents itself as a compact needle of light, its nucleus, perhaps only a few kilometers across, sufficient to generate the coma and tail we see, but modest beside the giants of our own system. SWAN R2, by comparison, performs as a spectacle of scale. Its coma blankets degrees of sky, while its tail, reported at lengths of 2 degrees or more, unfurls across millions of kilometers. Its filaments are gossamer thin, densities approaching vacuum, yet its sheer expanse makes it visible across interplanetary space. And so the visual poetry of their convergence plays out against the turning of Earth's seasons. As autumn deepens across the northern hemisphere, both comets sink toward the western horizon after sunset. There, SWAN R2 dominates the scene, a brilliant arc rising in Virgo, visible to anyone with a clear view and a simple pair of binoculars, an alien fire scrawled across the autumn dusk. 3I Atlas demands more serious equipment to glimpse, yet once found its green tint makes it impossible to mistake. But October offers obstacles as well as opportunities. The same orbital geometries that bring these visitors so near to the sun also conspire against us, drowning them in solar glare just as their stories grow most compelling. As both comets approach perihelion, Earth-based telescopes will steadily lose them, leaving astronomers blind through the very weeks when their behavior will be most intense. This blackout is more than an inconvenience. It is a gap in knowledge that may prove decisive in understanding what these wanderers truly are. For it is in these hidden weeks, under the furnace of solar heating, that anything unusual, any secrets concealed in their cores will most likely make themselves known. The retrograde course of 3I Atlas adds still deeper complexity. Moving against the direction of the planets, its orbit subjects it to unique gravitational nudges, perturbations that can subtly alter its trajectory over time. If astronomers can track the object with sufficient precision before and after its solar passage, those deviations could become a tool, hinting at its mass and even its internal structure. On the 3rd of October, Mars takes the role of advanced sentinel. The red planet, already ringed by robotic explorers built to study its weather and geology, will turn its instruments opportunistically toward the passing visitor. These spacecraft were not designed for interstellar comets, but in this rare alignment, they may become our clearest witnesses. The European Space Agency has confirmed plans for Mars-based observations using the ExoMars Trace Gas Orbiter and other orbiters circling the planet. With spectrometers and high-resolution cameras, they may capture details of coma formation and tail evolution that Earth cannot see, perspectives unlocked by Mars's fortuitous vantage point. Together, Earth and Mars weave a stereo vision of the encounter, two worlds lending their eyes to the same fleeting target. Yet even with multiple viewpoints and advanced tools, the deepest questions refuse to yield. The timing gnaws at the minds of researchers. In a universe where chance alignments are measured in spans of millions of years, why should two such different visitors arrive so close together in the same season of observation? Statistically improbable and yet undeniable, their parallel journeys press the imagination into uneasy territory. If two paths rhyme, does that rhyme belong to the poetry of chance or to the design of something greater? Human beings are wired to see patterns, to carve meaning from noise and purpose, from randomness. So when two cosmic visitors arrive at the Sun within weeks of one another, each bearing unusual traits and tracing paths that appear almost choreographed, our imaginations inevitably begin to write stories far larger than the raw data can justify. These narratives range from the exotic to the extraordinary, offering different lenses through which to view the convergence of October 2025. One such vision is the Scout and Fortress hypothesis. In this telling, 3I Atlas is the probe, sleek, swift, maneuverable, its task to reconnoiter, to map resources, and test the defenses of our solar system. SWAN R2 becomes the installation, a base or relay, capable of sustaining longer operations in the inner system. Their timing is not coincidence, but coordination. Phases of a mission set in motion years, or even decades ago, in the silent dark between the stars. Another interpretation casts them as part of an ancient maintenance cycle. Perhaps they are relics of an automated infrastructure, machines on scheduled runs to service equipment scattered across our galactic neighborhood. In this script, 3I Atlas could be the courier of updates or replacement parts, while SWAN R2 provides power or raw materials for repairs. Our solar system, in this view, is simply a waypoint on a cosmic service route. The ancient patrol hypothesis pushes deeper into speculation. Here, these bodies are fragments of a long-dormant monitoring web, seeded millions of years ago by a civilization wary of emergent threats. With humanity's radio signals leaking into space over the last century, radar, broadcasts, satellites, those silent sentinels may have stirred awake, dispatching reconnaissance craft and heavier platforms to examine the sudden rise of technological intelligence on Earth. Perhaps most provocatively, some argue the visitors are not scouts but replies. For decades, our electromagnetic chatter has been expanding outward at light speed, an unintentional beacon announcing our arrival to the galaxy. If anyone was listening, then 3I Atlas and SWAN R2 may be their answer, arriving not by chance but as a direct response to our technological awakening. Other theories stretch even further. The relic technology hypothesis imagines they are artifacts of our own descendants, launched in some far future age when humanity has mastered interstellar flight, then sent back through space, or even time, designed to appear at precise moments in our history. Their odd chemistry and puzzling orbits could reflect materials and methods beyond our comprehension, yet still recognizably human in origin. Still others look backward instead of forward, reaching into myth. Across cultures, comets and strange lights in the heavens have long been read as harbingers, omens of kings rising and falling, prophets arriving, or ages ending. Perhaps 3I Atlas and SWAN R2 are modern echoes of those archetypal signs, punctuation marks in the unfolding narrative of human development. And then there is the most ominous tale, the predator and guardian. In this frame, 3I. Atlas is no benign wanderer but a weapon, an instrument of invasion. SWAN R2 then becomes the countermeasure, either dispatched by the same makers as a safeguard against their own technology, or sent by an entirely different intelligence determined to neutralize the threat. Under this interpretation, October of 2025 is not just a celestial coincidence, but a battlefield written across the sky, with Earth as the silent prize at its center. Speculative frameworks take root partly because they confront a basic limitation of astronomy itself, the discipline's default assumption that the unusual must be natural. That principle has carried science far, unlocking stellar evolution, black holes, and the expanding universe. Yet it also risks creating blind spots, dismissing exotic possibilities, not because they are disproven, but because they fall outside accepted theory. Harvard astronomer Avi Loeb, who stirred worldwide debate by suggesting that 1I Oumuamua might be artificial, has extended similar reasoning to 3I Atlas. He notes the strange chemistry, the uncanny timing of its solar approach, and the apparent coordination with SWAN R2 as possible signs of technology rather than nature. His arguments stress a balance. Extraordinary claims demand extraordinary evidence, but extraordinary evidence, when it appears, deserves serious consideration. NASA and the European Space Agency hold to more cautious interpretations. Their scientists emphasize that, so far, the data still fits natural explanations, however unusual the details. They point out that our sample of interstellar visitors is tiny, only 3 confirmed in 6 years, hardly enough to define what counts as normal for such objects. The tension reflects deeper questions. How anomalous must an observation be before it forces us to reconsider our most basic assumptions? How do we weigh caution against the risk of overlooking discoveries that could reshape our understanding of the cosmos? Public debate, amplified by media and social platforms, often distorts the balance. The nickel without iron anomaly has been turned into breathless speculation about industrial processes and artificial manufacture, leaps far beyond what the spectra actually show. Meanwhile, the genuinely puzzling aspects, the volatile chemistry, the near-simultaneous timing, the parallel arrival of SWAN R2 draw less attention, despite being anchored in hard data. Conspiracy thinking thrives in such gaps. Human minds are primed to see agency in coincidence, to imagine intention in randomness, especially when the stakes touch our future. The idea that visitors are sent, not stumbled upon, satisfies deep needs for meaning in an indifferent universe. History offers both warning and inspiration. Every radical discovery, heliocentrism, black holes, exoplanets, was first greeted with skepticism. Yet history also shows that extraordinary claims without extraordinary evidence eventually fade, leaving behind cautionary tales of speculation outrunning proof. October 2025 offers a rare test. If 3I Atlas and SWAN R2 are natural comets, their perihelion behavior should align with the physics of sublimating ice and streaming dust. If not, deviations will reveal themselves. But here lies the difficulty. The very solar glare that makes perihelion so scientifically rich also blinds Earth's telescopes. During their closest encounters, the comets will vanish behind the sun, leaving only silence where data should be. We will be left to infer what occurred based on what emerges afterward, if they emerge at all. This gap is fertile ground for speculation. In the absence of measurement, imagination fills the void. The October silence may reveal as much about human psychology as about the visitors themselves. Still, whatever their nature, this convergence is a genuine scientific gift. Whether 3I Atlas and SWAN R2 are exotic iceballs or emissaries of something stranger, they expand our sense of what may dwell in the gulfs between stars and what occasionally drifts into our cosmic neighborhood. The stories we craft around them say as much about our fears and our hopes as about the comets themselves, And perhaps that is fitting. Are they comets? Fortresses? Or the long-awaited reply to a message humanity never knew it had sent? The story of 3I Atlas begins not with fireworks, but with a single pixel flickering on a CCD detector under the clear skies of Chile's Atacama Desert. On the 1st of July, 2025, the object finally grew bright enough for our automated sky surveys to notice it against the ancient tapestry of stars. The Atlas survey, the Asteroid Terrestrial Impact Last Alert System, uses 4 robotic telescopes, guardians built to detect asteroids that might one day threaten Earth. Night after night, these machines sweep their assigned sectors, comparing fresh images against catalogues of the familiar, flagging anything that moves, brightens, or appears where nothing existed before. At Rio Hurtado, one such sentinel captured the faint smudge that would become 3I Atlas. In itself, it was nothing remarkable, just a dim mark sliding across the stellar grid. But motion tells stories, and when astronomers traced its path, the mathematics delivered a revelation. This was no bound member of the solar family. Its trajectory was hyperbolic, an escape curve, the hallmark of an object destined to pass our sun only once before vanishing forever into the dark. Orbital mechanics divide the universe neatly, ellipses for those who belong, hyperbolas for those who are only passing through. 3I Atlas belongs to the latter, marking only the 3rd confirmed interstellar visitor in all of recorded history. Its orbit speaks of origins far from here. Inclined at roughly 175 degrees, it cuts beneath the plane of the planets, moving retrograde against the current of the solar system, like a salmon swimming upstream. Such a path is the fingerprint of formation elsewhere, in a star system with conditions unlike our own, followed by millions of years drifting through interstellar night before it reached our neighborhood. The discovery timeline shows how close we came to missing it. Interstellar objects arrive from arbitrary directions, often lurking in regions of sky too near the sun to be visible. By the time Atlas spotted it, the visitor had already crossed into the inner solar system, slipping past Jupiter's orbit and beginning its run toward the Sunday. Backtracking suggests it had been with us since early 2025, perhaps even late 24, faint and quiet until solar heat coaxed its first signs of activity. The delay underscores a truth. We only find such wanderers when they choose, by brightness and by geometry, to let themselves be found. Current projections place perihelion, the closest solar approach, on the 29th or 30th of October, at a distance between 1.35 and 1.4 astronomical units. That is just inside the orbit of Mars, closer to the Sun than any other interstellar object we have ever observed. On the 3rd of October, it will also brush past Mars itself at a distance of 30 million kilometers. In cosmic terms, that is close enough for orbiting spacecraft designed for Martian weather and geology to turn their instruments toward the interloper. The European Space Agency has already outlined preliminary plans to enlist these Martian eyes in the effort. For Earth, the passage is distant and safe. The comet comes no nearer than 1.8 astronomical units, or 270 million kilometers, close enough for powerful telescopes to study, but far enough to pose no risk. As for its size, uncertainty reigns. Observations from the Hubble Space Telescope on the 21st of July constrained the nucleus to perhaps only a few kilometers across. Modest by cometry standards, yet large enough to account for the activity we see. But brightness deceives. What we observe is not the nucleus itself, but sunlight scattering off dust and gas in the surrounding coma. Pinning down true dimensions demands careful modeling, the balance between how much sunlight the surface reflects and how much volatile material sublimates into space. Until then, the size of 3I Atlas remains another piece of the mystery, small on the cosmic stage, yet vast enough to reshape the stories we tell about what drifts in from beyond the stars. The campaign surrounding 3I Atlas ranks among the most concentrated observational efforts ever devoted to an interstellar visitor. The Hubble Space Telescope has delivered high-resolution imagery, charting subtle changes in the coma's shape and brightness across time. In August, the James Webb Space Telescope turned its infrared gaze upon the comet, unlocking chemical details inaccessible to any ground-based eye. Meanwhile, the Very Large Telescope in Chile dissected its light into spectral lines, identifying the precise atoms and molecules glowing in its atmosphere. Together, these efforts confirmed the peculiar chemical story: strong nickel lines, unaccompanied by iron, prominent cyanogen features, and a striking dominance of carbon dioxide signatures that have made 3I Atlas as fascinating to the public as it is to scientists. Even now, multiple space telescopes keep watch as the comet approaches its October milestones. But the window narrows. Growing distance and increasingly poor elongation angles will soon render Earth-based study impossible, leaving the last clear perspectives to spacecraft orbiting Mars during the brief passage. The scale of international coordination underscores how astronomy has become a global enterprise. Observatories in Chile follow the object through southern skies, handing off seamlessly to facilities in Hawaii and the Canary Islands as Earth rotates. Space-based observatories, free from night and weather, maintain continuity across the gaps. Yet perhaps the most revealing aspect of this discovery is what nearly slipped past us. For months, perhaps longer, the interstellar visitor drifted unnoticed, its faintness and geometry hiding it in the glare. How many others have crossed unseen, too small or too inert to display the comas that betray their presence? Objects lacking dramatic outgassing may remain invisible unless they skim dangerously close to the sun, while those arriving along certain lines of sight could stay cloaked in solar brilliance from arrival to departure. Models suggest that for every one we detect, dozens, perhaps hundreds, may pass without record. In that sense, 3I Atlas is not just a singular find, but a glimpse into a hidden population of wanderers threading the solar system at all times. Now, as October 2025 advances, 3I Atlas presses onward toward perihelion. Amateur observers with modest telescopes can already track its emerald-tinged coma, a ghostly lantern in the autumn sky, reminding us that our solar system is less fortress than thoroughfare. Before the comet disappears into the solar blaze, Mars stands as our front-row witness, its orbiters poised to record whatever secrets this traveler reveals. The unresolved question lingers: will our instruments on Earth, in orbit, and around Mars prove capable of distinguishing the exotic from the extraordinary in the fleeting window we have left to study this remarkable wanderer from the stars? The universe tells its stories in light, and since its discovery, 3I Atlas has been painting its tale in shades of green. As this interstellar traveler nears the sun, the heat awakens its frozen heart, releasing gases that have slept in ice for millions of years. Yet the colors blooming around its nucleus do not quite match the palette of comets born in our own solar system. The emerald glow that has enchanted observers across the globe emerges from a delicate interplay of chemistry and physics in the near vacuum surrounding the comet's core. Molecules excited by solar ultraviolet radiation, or by collisions within the coma, radiate at fixed wavelengths, fingerprints carved by the quantum structure of their electrons. For green, the usual suspects are diatomic carbon and cyanogen, both fluorescing brilliantly in sunlight. Reports in Live Science highlighted these possibilities, noting that while diatomic carbon remains the prime candidate consistent with past cometary observations, the precise molecules behind 3I Atlas's glow await confirmation from high-resolution spectroscopy. The distinction matters, for each molecule carries a different story about the environment where this comet was born. Cyanogen, though among the most toxic compounds known, glows with ghostly beauty in space, and its spectral presence offers clues to the organic chemistry of the stellar nursery that shaped this visitor. Its abundance relative to other carbon-bearing molecules encodes the temperatures, pressures, and reactions that unfolded billions of years ago around a distant star. But the green shimmer is only the surface of a deeper puzzle. When the Very Large Telescope in Chile dissected the comet's spectrum, it revealed fingerprints that strain our expectations. Strong nickel lines appeared, yet the iron that should have accompanied them was absent. On Earth, in meteorites, and throughout cosmic chemistry, nickel and iron march together in ratios set by the nuclear forges of stars. The periodic table's abundance patterns insist they should appear side by side. 3I Atlas, however, defies this law. The VLT observations, taken during its inbound phase, displayed nickel glowing at 588 nanometers, a sharp green signature against the noisy tapestry of cometary light. The same sensitive instruments sought iron at nearby wavelengths and found nothing. The limits were so strict that if iron had been present in ordinary cosmic amounts, it would have shone easily. To explain this anomaly, theorists suggest nickel-rich organics, frozen stable in interstellar night, may decompose near the Sun, releasing nickel first. Others point to space weathering across millions of years, altering surface chemistry in ways we do not yet understand. The wider chemical portrait, sketched by multiple observatories, reinforces the strangeness. James Webb Space Telescope, using its near-spec instrument, revealed a body dominated by carbon dioxide, with water vapor surprisingly scarce in its early activity. This balance suggests formation in a colder, more volatile-rich environment than the cradle of Earth and its planetary siblings. Different stars, with different temperature gradients, seed comets with chemistries unfamiliar to our system. European Space Agency teams analyzing the infrared data note that the low water-to-carbon dioxide ratio at large distances is consistent with early activation, when the most volatile ices ignite first. As 3I Atlas falls inward, water vapor should eventually grow more prominent once solar heat penetrates to less volatile ices. Measuring the changing production rates of each gas offers another keyhole through which to glimpse the nature of this traveler, a chemical diary unfolding line by line as it approaches the Sunday. As 3I Atlas draws closer to the Sun, its activity intensifies. Water vapor, carbon dioxide, cyanogen, and other volatiles stream outward in increasing quantities, their production rates rising predictably with decreasing distance from the star. These curves follow the textbook expectations for sublimating ices, strong evidence that what we are witnessing is governed by natural physics, not engineered emissions. And yet, within this framework of order, subtle deviations persist, enough to hold researchers' attention. The ratios between different molecules fail to align neatly with models derived from solar system comets. The comet's brightness, too, fluctuates in patterns that suggest either patches of varied composition across the nucleus or sudden jets erupting from subsurface processes still poorly understood. Amateurs play a vital role in tracking these changes. Skilled observers scattered across the globe contribute images of coma color, tail growth, and overall brightness, building continuous records that professional observatories, bound by schedules and limited telescope time, cannot replicate. Their efforts complement the detailed spectroscopy gathered by giants like Hubble, Webb, and the Very Large Telescope. But social media, eager for drama, sometimes distorts the science. The nickel without iron anomaly has been recast by some as evidence of industry or design, claims that leap far beyond what the spectra justify. NASA counters firmly that 3I Atlas remains consistent with a natural cometary origin, unusual but not unprecedented. Agency scientists remind us that comets born under alien conditions, different stellar chemistries, temperatures, and pressures should not be expected to mirror the compositions we know from our own Oort cloud. Here, the distinction between exotic and extraordinary becomes essential. Exotic chemistry is strange, perhaps unique, but explainable by the laws of physics. Extraordinary chemistry would hint at something crafted, something artificial. 3I Atlas, for now, sits firmly in the exotic camp. Whether it crosses the threshold into the extraordinary remains unresolved, an open question for continuing debate. History helps temper the narrative. Comet 2I Borisov, our previous interstellar guest, displayed its own oddities. Its carbon monoxide to water ratio baffled researchers until deeper analysis showed it could be explained by formation in a colder, more distant zone of its home system. Likewise, the Very Large Telescope's analysis of 3I Atlas has already suggested natural pathways for the nickel anomaly. One scenario invokes nickel-carbonyl compounds complexes that could form when nickel dust reacts with carbon monoxide in the cold interstellar medium, releasing nickel more readily than iron under solar heat. But October 2025 brings urgency. As solar heating ignites the comet's chemistry, Earth-based viewing grows more difficult, geometry conspiring to hide it in glare. In this narrow window, data must be gathered quickly before the object slips beyond reach, and so a deeper question emerges. What if this ignition we attribute to chemistry is something more, protocols activating according to a design we do not yet perceive? The molecules do not betray intent. They glow with the quantum precision of physics itself, indifferent to whether they were forged in nature's furnace or by intelligence unknown. In their light, we glimpse only the riddle, not the answer. The universe tells its stories in light, and since its discovery, 3I, Atlas has been painting its tale in shades of green. As this interstellar traveler nears the sun, the heat awakens its frozen heart, releasing gases that have slept in ice for millions of years. Yet the colors blooming around its nucleus do not quite match the palette of comets born in our own solar system. The emerald glow that has enchanted observers across the globe emerges from a delicate interplay of chemistry and physics in the near vacuum surrounding the comet's core. Molecules excited by solar ultraviolet radiation or by collisions within the coma radiate at fixed wavelengths, fingerprints carved by the quantum structure of their electrons. For green, the usual suspects are diatomic carbon and cyanogen, both fluorescing brilliantly in sunlight. Reports in Live Science highlighted these possibilities, noting that while diatomic carbon remains the prime candidate consistent with past cometary observations, the precise molecules behind 3I Atlas's glow await confirmation from high-resolution spectroscopy. The distinction matters, for each molecule carries a different story about the environment where this comet was born. Cyanogen, though among the most toxic compounds known, glows with ghostly beauty in space, and its spectral presence offers clues to the organic chemistry of the stellar nursery that shaped this visitor. Its abundance relative to other carbon-bearing molecules encodes the temperatures, pressures, and reactions that unfolded billions of years ago around a distant star. But the green shimmer is only the surface of a deeper puzzle. When the Very Large Telescope in Chile dissected the comet's spectrum, it revealed fingerprints that strain our expectations. Strong nickel lines appeared, yet the iron that should have accompanied them was absent. On Earth, in meteorites, and throughout cosmic chemistry, nickel and iron march together in ratios set by the nuclear forges of stars. The periodic table's abundance patterns insist they should appear side by side. 3I Atlas, however, defies this law. The VLT observations, taken during its inbound phase, displayed nickel glowing at 588 nanometers, a sharp green signature against the noisy tapestry of cometary light. The same sensitive instruments sought iron at nearby wavelengths and found nothing. The limits were so strict that if iron had been present in ordinary cosmic amounts, it would have shone easily. To explain this anomaly, theorists suggest nickel-rich organics, frozen stable in interstellar night, may decompose near the sun, releasing nickel first. Others point to space weathering across millions of years, altering surface chemistry in ways we do not yet understand. The wider chemical portrait, sketched by multiple observatories, reinforces the strangeness. James Webb Space Telescope, using its near-spec instrument, revealed a body dominated by carbon dioxide, with water vapor surprisingly scarce in its early activity. This balance suggests formation in a colder, more volatile-rich environment than the cradle of Earth and its planetary siblings. Different stars, with different temperature gradients, seed comets with chemistries unfamiliar to our system. European Space Agency teams analyzing the infrared data note that the low water-to-carbon dioxide ratio at large distances is consistent with early activation, when the most volatile ices ignite first. As 3I Atlas falls inward, water vapor should eventually grow more prominent, once solar heat penetrates to less volatile ices. Measuring the changing production rates of each gas offers another keyhole through which to glimpse the nature of this traveler, a chemical diary unfolding line by line as it approaches the Sunday. As 3I Atlas draws closer to the Sun, its activity intensifies. Water vapor, carbon dioxide, cyanogen, and other volatiles stream outward in increasing quantities, their production rates rising predictably with decreasing distance from the star. These curves follow the textbook expectations for sublimating ices, strong evidence that what we are witnessing is governed by natural physics, not engineered emissions. And yet, within this framework of order, subtle deviations persist, enough to hold researchers' attention. The ratios between different molecules fail to align neatly with models derived from solar system comets. The comet's brightness, too, fluctuates in patterns that suggest either patches of varied composition across the nucleus or sudden jets erupting from subsurface processes still poorly understood. Amateurs play a vital role in tracking these changes. Skilled observers scattered across the globe contribute images of coma color, tail growth, and overall brightness, building continuous records that professional observatories, bound by schedules and limited telescope time, cannot replicate. Their efforts complement the detailed spectroscopy gathered by giants like Hubble, Webb, and the Very Large Telescope. But social media, eager for drama, sometimes distorts the science. The nickel without iron anomaly has been recast by some as evidence of industry or design, claims that leap far beyond what the spectra justify. NASA counters firmly that 3I Atlas remains consistent with a natural cometary origin, unusual but not unprecedented. Agency scientists remind us that comets born under alien conditions, different stellar chemistries, temperatures, and pressures should not be expected to mirror the compositions we know from our own Oort cloud. Here, the distinction between exotic and extraordinary becomes essential. Exotic chemistry is strange, perhaps unique, but explainable by the laws of physics. Extraordinary chemistry would hint at something crafted, something artificial. 3I Atlas, for now, sits firmly in the exotic camp. Whether it crosses the threshold into the extraordinary remains unresolved, an open question for continuing debate. History helps temper the narrative. Comet 2I Borisov, our previous interstellar guest, displayed its own oddities. Its carbon monoxide to water ratio baffled researchers until deeper analysis showed it could be explained by formation in a colder, more distant zone of its home system. Likewise, the Very Large Telescope's analysis of 3I Atlas has already suggested natural pathways for the nickel anomaly. One scenario invokes nickel-carbonyl compounds complexes that could form when nickel dust reacts with carbon monoxide in the cold interstellar medium, releasing nickel more readily than iron under solar heat. But October 2025 brings urgency. As solar heating ignites the comet's chemistry, Earth-based viewing grows more difficult, geometry conspiring to hide it in glare. In this narrow window, data must be gathered quickly, before the object slips beyond reach, and so a deeper question emerges. What if this ignition we attribute to chemistry is something more, protocols activating according to a design we do not yet perceive? The molecules do not betray intent. They glow with the quantum precision of physics itself, indifferent to whether they were forged in nature's furnace or by intelligence unknown. In their light, we glimpse only the riddle, not the answer. Any departure from the expected patterns could hint at more exotic explanations for this visitor's behavior. Yet it is crucial to keep expectations grounded. The Mars flyby will not deliver close-range contact. 3I Atlas will remain tens of millions of kilometers away. No samples will be taken, no surface mapped, no secrets of internal structure revealed. What the encounter does offer is something subtler, a proof of concept, a rehearsal for how humanity might study future interstellar wanderers. The techniques refined during this passage: coordinated observations from orbiting spacecraft, carefully scripted pointing sequences, Contingency planning may become the foundation for more sophisticated campaigns when the next emissary from another star system arrives. Mission planners acknowledge the risks. Technical failures, communication dropouts, or poor viewing geometry could blunt or even erase the science return. Earth-based observatories provide a measure of redundancy, but as the flyby nears, solar glare and atmospheric interference increasingly undermine their utility. The true heart of the campaign lies compressed into a few hours, perhaps a few days, bracketing the closest approach. In that window, our mechanical emissaries circling Mars will turn outward, away from the planet they were built to study, and focus instead on a traveler born beneath another Sunday. If Mars could listen across the electromagnetic spectrum during those critical hours, what stories might it overhear? The instruments will strain with the patience of machines and the curiosity of their human makers, catching photons that whisper across millions of kilometers. In those patterns of light may lie the messages of a wanderer from the stars. But first, 3I Atlas must keep its appointment with the solar system's fourth planet, gliding past under the watchful eyes of our Martian sentinels before vanishing toward its final rendezvous, swallowed by the blinding glare of the Sunday. While 3I Atlas drew headlines as the exotic wanderer from interstellar space, another traveler was quietly preparing to eclipse it in spectacle. Comet C 2025 R2, better known as SWAN R2, emerged from the depths of our own solar system, dazzling observers with one of the most brilliant cometary displays in recent memory. Its story begins not in a grand observatory, but on the computer screen of amateur astronomer Vladimir Bezugli, who spent long hours poring over imagery from the SWAN instrument aboard the Solar and Heliospheric Observatory. On September 11, 2025, his persistence bore fruit. Amid the shifting glow of solar interference, he spotted an anomalous brightening soon confirmed as a new comet racing toward its solar encounter. SWAN, the Solar Wind Anisotropes instrument, was never designed as a comet hunter. Its purpose is to map hydrogen atoms produced when solar ultraviolet light tears apart water molecules drifting through space, a process that reveals the shape and flow of the solar wind. Yet in doing so, it also makes hidden comets visible, flagging activity that conventional telescopes miss when objects lie too close to the sun's glare. SWAN R2's sudden appearance after solar conjunction highlights this very challenge. Long-period comets often sneak in from behind the sun, their visibility masked until geometry shifts. This phenomenon, known as the Holacek effect, explains why many of history's brightest comets seem to materialize suddenly, already ablaze. The comet's official designation C2025 R2 follows the International Astronomical Union's strict system. C marks it as a long-period object, almost certainly from the far-flung Oort cloud. The year denotes its discovery, while R2 shows it was the second comet logged in the latter half of September. But numbers and letters cannot capture the splendor witnessed from Earth. By mid-September, SWAN R2 had crossed the threshold of naked-eye visibility, glowing at magnitude 6 under dark skies. Unlike many comets that peak and fade, this one kept growing brighter after its solar encounter. Astronomy Picture of the Day, on September 16th, showcased the newcomer, visible in binoculars, its tail lengthening rapidly, a gift for astrophotographers across the globe. Its proximity to the bright star Spica in Virgo provided a beacon for backyard stargazers, guiding them toward a vision from the outer solar system. Reports soon described a tail stretching up to 2 degrees across the sky, 4 times the apparent diameter of the full moon, a structure millions of kilometers long, painted in dust and gas. Unlike the interstellar trajectory of 3I Atlas, SWAN R2 traces a vast elliptical orbit. It spends decades or centuries in the frozen realms beyond Neptune before being nudged sunward, where heat awakens its ices. Perihelion came on September 12th, when it skimmed within half an astronomical unit of the Sunday. Intense solar radiation boiled its surface, releasing the clouds of dust and vapor that sculpt its coma and sweeping tail. Its closest approach to Earth is expected on October 21st, 2025, when it will pass within 0.27 astronomical units, about 40 million kilometers, a safe but close enough distance to make it a prime target. The timing is remarkable, aligning almost exactly with 3I Atlas's own dramatic solar passage. As September waned, brightness estimates placed SWAN R2 at magnitude 6 to 7, readily visible with binoculars and verging on naked-eye brilliance under pristine skies. The steady brightening of SWAN R2 suggests it could reach magnitude 4 or 5 by the time of closest approach to Earth, placing it among the brightest comets of 2025. For skywatchers in the southern hemisphere, evening skies will offer the most favorable views, though observers in the northern hemisphere can still trace it low along the western horizon after sunset. The comet's shifting position relative to the ecliptic and its motion against Earth's orbit create changing geometries that alter how and where it can be seen throughout its apparition. Amateur astronomers worldwide have rallied to document its progress, building a living, real-time database that complements professional studies. Skilled astrophotographers have already captured intricate structures in its tail, including dramatic disconnection events, moments when interactions with the solar wind's magnetic field sever a section of the ion tail, leaving it adrift before the comet forges a new one. These images provide dynamic evidence of how fragile and ever-changing cometary forms truly are. Yet uncertainties linger. Because SWAN R2 has been observed for only a short arc of its orbit, its exact path remains imprecise. Comets are notorious for experiencing non-gravitational nudges as outgassing jets subtly adjust their trajectories. Until more data accumulates, long-term predictions remain provisional. The Minor Planet Center continues to refine orbital solutions with new astrometric measurements, streaming in from observatories around the world. These refinements will eventually determine whether SWAN R2 is bound to a closed elliptical orbit, destined to return in millennia, or whether this passage will fling it permanently into the interstellar dark. Safety assessments remain reassuring. At its closest, the comet will pass within 0.27 astronomical units, about 40 million kilometers comfortably distant, posing no threat to Earth while offering an excellent opportunity for study. Standard monitoring protocols remain in place, watching for any deviations that might alter those projections. Meanwhile, the comet's striking appearance has made it a favorite for outreach and education. Astronomy clubs and planetariums across the globe have woven SWAN R2 into their programs, using its spectacle to teach about comet formation, solar system architecture, and the restless processes that sculpt our cosmic environment. Professional observatories, too, are now training spectrographs and photometers on the comet, though the bulk of telescope time remains devoted to 3I Atlas because of its interstellar pedigree. Still, SWAN R2 provides crucial insights into the behavior of icy bodies from our own Oort cloud, allowing scientists to study how local comets respond to solar heating under nearly identical conditions. The timing is extraordinary. Two wildly different emissaries, one forged in another star system, the other from the frozen reservoir surrounding our own, now blaze through the inner solar system almost side by side. Both are subjected to the same solar furnace, yet each carries the imprint of its birthplace. For astronomers, this cosmic coincidence offers a rare comparative experiment. How does environment shape the chemistry, brightness, and behavior of a comet? And for the rest of us, it offers something more poetic. If 3I Atlas is the scout, probing quietly into our neighborhood, then SWAN R2 arrives as a herald, a city-sized banner unfurled across the sky, as if announcing that something larger is at play. The universe rarely arranges such juxtapositions, but October 2025 may become remembered as the month when the heavens placed two mirrors side by side, one reflecting the mysteries of distant stars, the other reminding us of the enigmas born in our own backyard. The boundary between the exotic and the engineered is often thin in speculative astronomy, where unusual data can spark extraordinary theories about what might be possible in a universe, perhaps already inhabited by intelligences we have yet to recognize. 3I Atlas and SWAN R2 present features that, though consistent with natural explanations, invite more daring interpretations, thought experiments in propulsion, energy control, and the physics of intention written into the motion of cosmic bodies. Begin with propulsion. Natural comets obey gravity alone, their paths carved by the inverse square law, their journeys dictated by the forces of their birth or their violent ejection from distant systems. A true propulsion system, by contrast, would betray itself through deviations from this predictable dance, steady accelerations, vector shifts, or course corrections that defy the principles of ballistic motion. A plasma drive, venting ionized gas at tremendous speeds, would leave behind glowing exhaust plumes, spectral fingerprints shaped by the temperature and composition of the expelled material. More importantly, such thrust would accumulate into clear violations of Keplerian orbits, measurable over time. 3I Atlas shows none of these signs. Its hyperbolic arc follows precisely the track expected of an object unbound to the sun, with brightness and spectra that rise and shift predictably as it falls inward. The outgassing seen through our most sensitive instruments matches the ordinary sublimation of ices under solar heat, and yet the precision of its timing lingers in the mind. To arrive near Mars and Earth within weeks of SWAN R2's own closest approach strains the mathematics of probability. If coincidence gives way to coordination, then the propulsion required must operate with such subtlety that it remains invisible to every tool we possess. Electromagnetic shielding provides another avenue for speculation. Comets naturally generate plasma sheaths as solar windrakes across their ionized comas, sculpting magnetic structures that deflect charged particles and stretch ion tails away from the sunday. A deliberately engineered field could masquerade within this natural architecture, its difference lying not in appearance but in purpose, configurations optimized not for passive deflection but for communication, energy harvesting, or radiation protection. Yet here too, the instruments are silent. James Webb, alongside Earth's largest spectrographs, records nothing but the expected signatures of comet-solar-wind interaction. No anomalous emissions, no coherent signals, no evidence of fields tuned for anything other than natural physics. If such objects were part of scheduled patrols, their orbits would reveal intent patterns of return, coordinated arrivals, or modified trajectories that repeat strategically rather than randomly. But the evidence resists this. Since 2017, only 3 confirmed interstellar visitors have crossed our skies. 1I Oumuamua, 2I Borisov, and now 3I Atlas. No rhythm unites them, no cadence of deliberate spacing, no choreography suggesting a larger plan. Still, thought experiments persist. Avi Loeb's response to our signal hypothesis envisions a galaxy seeded with dormant monitoring systems, awakened by the faint bubble of our own electromagnetic leakage radio, television, radar spreading outward for a century. In this view, visitors like 3I Atlas might not be coincidences at all, but automated replies, dispatched long ago and triggered by the rising murmur of human civilization echoing into space. This line of reasoning, linking our technological dawn to the sudden arrival of unusual visitors, offers a compelling story. Yet NASA and the European Space Agency hold firmly to the data. Current observations, they emphasize, remain consistent with natural explanations. The chemistry, the orbits, the behavior of both 3I, Atlas, and SWAN R2 fall within the broad spectrum of cometary physics, even if they occupy the more exotic edges of that spectrum. The nickel without iron anomaly in 3I Atlas illustrates the tension perfectly. To some, it conjures visions of industry, selective processing, exhaust plumes rich in nickel but cleansed of iron, a chemical fingerprint of manufacture. But the Very Large Telescope's analysis reminds us that nature itself can mimic these patterns. Nickel-carbonyl chemistry, surface weathering over millions of years, and selective sublimation of ices all provide plausible natural routes to the same result. What appears engineered may in fact be the work of time and physics, indifferent and blind. Color changes and apparent switching on behavior add to the puzzle. As comets approach the sun, they brighten in irregular surges, different ices vaporizing at different distances, producing bursts of activity that resemble activation events. To the untrained eye, such transitions could look like propulsion systems powering up, but under careful analysis, they align with well-understood sublimation thresholds. Outgassing may be chaotic, yet its chaos follows the logic of solar heating. If an object were truly engineered, its signatures would extend beyond these natural irregularities. Sustained thrust would bend orbits in ways gravity cannot explain. Attitude control would leave brightness modulations as surfaces shifted deliberately toward or away from sunlight. Coherent radio signals would pierce the cosmic static with unmistakable structure. To test these possibilities, international monitoring networks have swept the skies. Radio arrays, radar dishes, sensitive photometers, the Very Large Array, successors to Arecibo, and other major facilities have all searched. Their verdict is silence. No structured transmissions, no anomalous accelerations, no electromagnetic beacons of intent. Radar echoes, faint and weak, return only what one expects from porous ice and dust, not from polished metal. Infrared studies tell the same story. Artificial structures, with heat sources, regulation systems, or exotic alloys, would glow differently under the sun's gaze. Instead, both 3I Atlas and SWAN R2 radiate as natural mixtures of ice and dust, warming passively, nothing more. The energy budgets required for genuine interstellar craft stretch credulity. Vast reserves to propel, to shield, to communicate across the void. Were such systems present, they would leave imprints in the spectrum. Instead, the instruments find only silence and sunlight. The astronomical community has established protocols for escalation procedures ready to activate if unmistakable signs of technology ever appear. Multiple independent detections, structured signals, unexplainable orbital patterns, any one of these would trigger concentrated global campaigns from NASA, ESA, and beyond. None have been activated. For now, consensus holds. Both 3I Atlas and SWAN R2 remain extraordinary but natural, their mysteries falling within the realm of physics rather than engineering. And yet absence of evidence is not evidence of absence. Technologies far beyond our comprehension might conceal themselves within natural behaviors, their signatures buried below our threshold of recognition. The epistemological gap between what we can measure and what might exist leaves a fertile space for speculation. Into that space steps the human mind, a pattern-seeking machine eager to find meaning. Two visitors, arriving almost simultaneously, during the very century when our species first reaches into space. Coincidence or choreography? The question lingers, irresistible, shaping stories that stretch beyond science into myth. Statistical studies of interstellar visitor rates suggest that the apparent clustering of strange arrivals in recent years may say more about us than about them. Our instruments have grown sharper, our surveys more comprehensive, our algorithms more attentive. Objects that would have slipped silently past in earlier decades are now caught, catalogued, and scrutinized. Since 2017, 3 interstellar visitors have been confirmed: 1I Oumuamua, 2I Borisov, and now 3I Atlas. Each carried mysteries that sparked speculation, yet each, under the weight of detailed analysis, yielded to natural explanations. The pattern reminds us that the unusual need not be unnatural. Exotic properties often stretch theory, but still fit within physics' wide embrace. Computer models of galactic dynamics reinforce this point. Simulations of ejected planetesimals suggest our solar system should be struck by natural wanderers at rates comparable to what we now observe, assuming reasonable densities in our local stellar neighborhood. In this light, the timing and character of recent detections fall well within expectations, and yet a lingering possibility remains that some fraction of these visitors are not merely natural, but technology so advanced it disguises itself in the familiar, indistinguishable from comets, perhaps by design, perhaps because any truly sophisticated engineering would bend to physical law rather than fight against it. Such artifacts would pass our scrutiny, invisible not because they are hidden, but because they are perfect in their mimicry. The ultimate test may arrive in October, as both 3I Atlas and SWAN R2 approach the Sunday perihelion is a crucible. Heat and radiation stress comets to their limits, peeling back layers, igniting outbursts, sometimes tearing nuclei apart. If any artifice lurked within, this would be the moment it might falter or reveal itself. Yet irony intervenes. During these very weeks, Earth's telescopes will be blinded by solar glare, unable to witness the critical hours. The gap in our coverage may coincide with the moment of greatest revelation. Mars provides the only consolation. As 3I Atlas swings within 30 million kilometers of the red planet, orbiters will attempt opportunistic observations. But these spacecraft were built for geology and weather, not for catching the signatures of machines cloaked as comets. Their instruments can track coma brightness, gas production, and tail geometry, but not the subtleties of engineered propulsion or concealed electronics. Even under perfect conditions, their vision may not pierce the veil. This brings us to the deeper question. The issue is not whether we have proof of artificial visitors, but whether we would recognize such proof if it lay before us. What should a machine look like after millions of years of interstellar drift? Would it glow like metal, radiating its own heat? Or would it appear exactly as it does now, dusty, icy, indistinguishable from the comets we know, save for details that tease our imagination? Perhaps what we are seeing already is the signature, anomalies just exotic enough to inspire debate, but natural enough to avoid crossing the threshold into extraordinary evidence. The universe does not surrender its secrets easily. It reveals them only to instruments precise enough, and to minds prepared to ask questions without easy answers. Some mysteries wait not for discovery, but for the evolution of observers able to perceive them. Until then, we watch, measure, and wonder, aware that the line between comet and construct may be thinner than our current science can trace. In the grand theater of space, coincidences invite suspicion, and timing transforms into choreography when human imagination seeks order in cosmic chaos. Two celestial visitors, arriving within weeks of each other, displaying complementary characteristics and converging on the sun in the same narrow window of time, such a scenario begins to feel less like chance and more like design, once speculation fills the silence where data cannot speak. Imagine, for a moment, that SWAN R2 is no ordinary comet but a mobile depot, while 3I Atlas serves as a nimble reconnaissance probe. In this framework, the sprawling, radiant body with its monumental tail becomes a logistics platform, its volatility a disguise for controlled systems of resource management and communication. The smaller, sharper visitor, 3I Atlas, plays the scout darting ahead to gather intelligence about our solar system, relaying its findings back to the larger installation. This pairing could explain some of the puzzles. The scout's precise timing and hyperbolic trajectory might not be random at all, but a navigation toward predetermined coordinates where SWAN R2 awaited, ready to receive data, transfer resources, or perform maintenance. The chemical signatures we read as exotic outgassing nickel without iron, carbon dioxide dominance, cyanogen traces could be byproducts of hidden systems under thermal stress, controlled emissions, fuel transfers, atmospheric processes at work. An alternative speculation suggests that both bodies are natural, but not untouched. In this version, they are commandeered platforms, comets, and asteroids hollowed or seeded long ago by an ancient monitoring network, distributed across our galactic neighborhood. Rather than purpose-built craft, they are piggybacked vessels, modified to awaken when a young civilization begins leaking electromagnetic signals into space. Their camouflage is perfect. They hide in plain sight among the countless icy wanderers, their artificial core cloaked by natural crusts of rock and volatile ice. The sun itself, may play a central role. Its light is an endless power source, its wind a river of plasma that could carry signals or energize technologies built on principles we have yet to discover. Surveillance grid scenarios envision networks of nodes anchored by stellar gravity wells, harvesting radiation, aggregating data, and relaying it across interstellar distances. From this perspective, the October convergence of two very different comets could be routine, a scheduled relay in a monitoring system far older than humanity. Yet darker interpretations exist. In the hunter and harvester dynamic, 3I, Atlas becomes a predatory agent, tasked with scouting and neutralizing threats, while SWAN R2 serves as the extractor, a processor waiting to consume what the scout delivers. The asymmetry between the compact probe and the vast, luminous depot reflects their complementary roles: precision and scale, reconnaissance and resource capture, predator and processor. Imagery rising from this speculation is cinematic. The small courier spirals inward on its rendezvous path, while the colossal installation unfurls hidden collectors and harvesting systems poised for whatever materials or messages the scout carries. Whether allegory or reality, the mind conjures a vision of choreography rather than coincidence, a cosmic operation unfolding in plain view under the guise of comets drifting through October skies. The cometary activity we record, the jets, the brightening, the sprawling tails, may simply be the surface disguise of far more purposeful operations: energy collection, matter conversion, even the assembly of temporary infrastructure to sustain extended missions in our celestial neighborhood. These possibilities remain wholly speculative, unsupported by direct evidence, yet they fascinate precisely because they impose narrative order on what otherwise appears chaotic and coincidental. Human cognition resists randomness. We seek design in the noise, intention in coincidence. The October clustering of cosmic milestones invites such storytelling. SWAN R2's perihelion on September 12th, 3I, Atlas's Mars flyby on October 3rd, SWAN R2's Earth approach on October 21st, and 3I, Atlas's perihelion at month's end. Together they form a sequence, a chain of dates and positions that could be read as either the dice rolls of chance or the careful timing of choreography. History supplies mythic precedents. Every civilization has read meaning into lights in the sky. Comets foretold the collapse of dynasties in China, the fall of kings in Europe, the births of prophets in the Near East. The dual arrival of 3I, Atlas and SWAN R2 fits neatly into these archetypes. Two heralds marking transition, two omens intertwined across the same stretch of heavens. And the refrain we return to, is it a comet, a fortress, or a reply to a message we never knew we sent, becomes even more resonant when applied to a pair rather than a solitary anomaly. If one is the message and the other the reply, then October 2025 might signify the closing of a communication loop that began decades ago, when our first radio signals escaped Earth's atmosphere. Yet at this juncture, caution is required. We are crossing from the solid ground of observation into the shifting waters of speculation. The data, the orbital mechanics, the chemistry, the production curves support natural explanations, even if they also inspire more exotic imaginings. To assume shared purpose is to project intelligence where none is proven, coordination where coincidence suffices. These frameworks reflect not only scientific curiosity, but also deep psychological needs for meaning in a universe that often seems indifferent. Still, one cannot entirely dismiss the possibility that technologies might exist so advanced they mimic natural processes seamlessly, operating within physical laws rather than against them. Such systems would elude our current methods of detection, revealing themselves only through subtleties our instruments are not yet capable of perceiving. The ultimate test will come in the furnace of perihelion. As both objects endure their closest solar approaches, stresses and energies may strip away disguises or trigger behaviors that betray their true nature. If coordination exists between scout and depot, scalpel and factory, It might manifest during these hidden weeks when the sun's glare blinds our telescopes. Ironically, the most decisive evidence may emerge precisely when we cannot watch. When the silence lifts and the comets re-emerge, we may find nothing more than refined data on natural sublimation and dust dynamics. Or we may face hints that force us to reconsider what moves through the interstellar dark. Until then, the question lingers. If two objects share a mission, what purpose requires both a blade and a forge? The answer, if it exists, may be written in the solar fire that now consumes them, leaving humanity only memory, speculation, and wonder. In the speculative theater, where astronomy collides with imagination, few frameworks shimmer with as much intrigue as the relay hypothesis. It casts 3I Atlas, not as a simple ice rock wanderer, but as a courier, an interstellar messenger carrying compressed archives of intelligence gathered during its long voyage through the galactic dark. SWAN R2, larger and more luminous, assumes the role of the processor, a mobile depot and transmission hub ready to receive, decode, and broadcast whatever payload its companion delivers. Their convergence near the Sun becomes the stage for an exchange that may have been scripted decades or centuries ago. Picture 3I Atlas first. Small, nimble, optimized for speed rather than storage. Its strange chemistry, the nickel without iron, the carbon dioxide dominance, translates in this vision not into exotic sublimation but into writing. Data inscribed into physical substrates, information encrypted in emissions masquerading as cometary outgassing. Each burst of gas could be less an accident of heating ice and more a deliberate transmission. Now, turn to SWAN R2, vast, spectacular, with a tail spanning millions of kilometers. What if that shimmering plume is camouflage, a screen of dust and ions concealing collectors, processors, even beam emitters? In this reading, its sprawling coma functions like an industrial veil, harvesting solar radiation, modulating plasma streams, perhaps even sculpting the solar wind itself into a communication medium. The sun then emerges not as backdrop, but as the third actor, the furnace, the amplifier, the gravitational lens that makes interstellar communication possible. Einstein's relativity predicts stars bend and focus light. Place a relay at just the right focal point, and a star becomes a galactic-scale telescope. Could the sun itself serve as part of an ancient network, a relay node where visitors converge to complete information exchanges? The physics of plasma offers another canvas, the solar wind as a carrier wave, its charged particles etched with encoded signals flowing outward across the heliosphere. The imagery writes itself. SWAN R2 unfurls, collectors disguised as dust sheets. 3I Atlas spirals inward, compressing terabytes into crystalline matrices resilient to radiation. Invisible beams thread across the corona, intelligence burning through ion fire, while the sun's energy bankrolls an operation photosynthesis would envy. The October 2025 timetable provides the choreography. Perihelion and close approaches align like pre-planned rendezvous points, optimal for both solar energy and geometry. Earth's expanding radio bubble, the electromagnetic leakage we've been emitting since the 1920 seconds, provides the inciting signal. 100 light-years across now, that bubble advertises our presence to any dormant network of monitors. The visitors, in this story, are the response. But reality remains stubborn. No narrowband radio signals have been detected. No anomalous thrusts or course corrections have revealed propulsion systems. Infrared profiles, orbital mechanics, emission curves, all sit within the realm of exotic but natural cometary physics. NASA and ESA repeat the mantra, extraordinary claims require extraordinary evidence, and for now, the evidence falls short. Still, the if true, who sent it? Question lingers like an echo. Perhaps these are archives from our own descendants, flung backward through time by technologies that bend causality. Perhaps they are the work of evolutionary cousins in distant systems, civilizations that rose millions of years before us and seeded the galaxy with quiet sentinels. Or perhaps they are nothing more than what they seem: comets, beautiful, fleeting, indifferent, onto which we project our hunger for meaning. Whatever the answer, the relay hypothesis transforms October 2025 into more than an astronomical coincidence. It becomes a test of imagination as much as instrumentation. Are we witnessing ice sublimating in sunlight, or the encrypted whispers of a network older than our species? The photons our telescopes record cannot tell us which story is true. They carry only light. The rest, for now, is interpretation. Not all visions of October's convergence require active intelligence, guiding 3I, Atlas, and SWAN R2. Some frameworks place both objects within a different, more haunting narrative. The possibility that we are witnessing the technological fossils of civilizations long gone. In this view, the two visitors are not scouts, messengers, or predators, but automated components of a monitoring grid established millions, even billions of years ago by species that reached interstellar capability and then either transcended or perished, leaving only their infrastructure behind. Machines without masters, systems without architects, still executing code long after the voices that wrote it fell silent. The practicality check for such a network highlights daunting physics. Broadcasting coherent, information-rich signals across interstellar distances requires energy expenditures on the scale of stellar luminosities. Receiving those signals demands arrays with effective apertures comparable to entire planets. By the yardstick of our engineering, the infrastructure necessary for galaxy-wide relay systems dwarfs anything we could realistically build. But this impossibility is only a reflection of our era's physics. Civilizations that mastered interstellar travel may have moved beyond energy paradigms we can even name. To them, our objections might sound like the skepticism of a caveman told that voices could someday be carried on invisible currents of air. This fossil network hypothesis carries a certain narrative satisfaction. It reframes random encounters as purposeful remnants, suggesting that our solar system is not merely a lonely corner of space, but a node, one of many within a network designed to catalogue, to listen, or to guide. Humanity's recent technological bloom, leaking radio waves into the void, might have awakened dormant systems, triggering automated handshakes written eons ago. To believe this is to believe we have crossed some threshold, that we are not ignored, and that somewhere, if not in minds, then in machines, we are noticed. Yet here lies the tension. The evidence before us remains stubbornly ordinary. Nickel without iron, carbon dioxide dominance, anomalous brightening curves, all exotic, yes, but still within the reach of natural cometry physics. To call them messages is to impose intention where coincidence suffices, to find agency where chemistry may already provide an answer. The October convergence sharpens the dilemma into a test. If any data transfer occurs, it would likely be timed with perihelion, when solar energy is at its peak, and when communication efficiency would be maximized. But during those very days, the glare of our own sun blinds our instruments. The moment of greatest possibility is also the moment of deepest observational silence. We may emerge from this October gap with nothing more than better models of sublimation curves and dust particle dynamics. Or we may confront data that hints, however faintly, that our star functions as a cosmic relay, a post office in a galactic network whose architects are dust. The question, then, is not only whether such a network exists, but whether we are capable of recognizing its operations at all. The relay hypothesis, whether of living intelligence or fossilized machinery, turns our sun from furnace into node, and our visitors from wanderers into couriers. It is a story we tell because it satisfies the deep human hunger for pattern and meaning. Whether the cosmos agrees with that story remains the mystery of October 2025. Not all visions of October's convergence require active intelligence guiding 3I, Atlas, and SWAN R2. Some frameworks place both objects within a different, more haunting narrative, the possibility that we are witnessing the technological fossils of civilizations long gone. In this view, The two visitors are not scouts, messengers, or predators, but automated components of a monitoring grid established millions, even billions of years ago by species that reached interstellar capability and then either transcended or perished, leaving only their infrastructure behind. Machines without masters, systems without architects, still executing code long after the voices that wrote it fell silent. The practicality check for such a network highlights daunting physics. Broadcasting coherent, information-rich signals across interstellar distances requires energy expenditures on the scale of stellar luminosities. Receiving those signals demands arrays with effective apertures comparable to entire planets. By the yardstick of our engineering, the infrastructure necessary for galaxy-wide relay systems dwarfs anything we could realistically build. But this impossibility is only a reflection of our era's physics. Civilizations that mastered interstellar travel may have moved beyond energy paradigms we can even name. To them, our objections might sound like the skepticism of a caveman told that voices could someday be carried on invisible currents of air. This fossil network hypothesis carries a certain narrative satisfaction. It reframes random encounters as purposeful remnants, suggesting that our solar system is not merely a lonely corner of space, but a node, one of many within a network designed to catalog, to listen, or to guide. Humanity's recent technological bloom, leaking radio waves into the void, might have awakened dormant systems, triggering automated handshakes written eons ago. To believe this is to believe we have crossed some threshold, that we are not ignored, and that somewhere, if not in minds, then in machines we are noticed. Yet here lies the tension. The evidence before us remains stubbornly ordinary. Nickel without iron, carbon dioxide dominance, anomalous brightening curves, all exotic, yes, but still within the reach of natural cometary physics. To call them messages is to impose intention where coincidence suffices, to find agency where chemistry may already provide an answer. The October convergence sharpens the dilemma into a test. If any data transfer occurs, it would likely be timed with perihelion, when solar energy is at its peak and when communication efficiency would be maximized. But during those very days, the glare of our own sun blinds our instruments. The moment of greatest possibility is also the moment of deepest observational silence. We may emerge from this October gap with nothing more than better models of sublimation curves and dust particle dynamics, or we may confront data that hints, however faintly, that our star functions as a cosmic relay, a post office in a galactic network whose architects are dust. The question, then, is not only whether such a network exists, but whether we are capable of recognizing its operations at all. The relay hypothesis, whether of living intelligence or fossilized machinery, turns our sun from furnace into node and our visitors from wanderers into couriers. It is a story we tell because it satisfies the deep human hunger for pattern and meaning. Whether the cosmos agrees with that story remains the mystery of October 2025. The sun burns with the fury of 4.5 billion years of fusion, every second converting millions of tons of matter into energy. Every breath we take dependent on its relentless output. We see it as anchor, furnace, and life-giver. But what if it is also a quarry? A gas station on a cosmic scale, visited not by chance wanderers, but by machines or systems designed to extract its hidden wealth on timescales measured not in human lifetimes, but in millennia. In this speculative framework, 3I, Atlas, and SWAN R2 are not random comets. They are workers in an ancient industrial ballet. The smaller visitor functions as surveyor and foreman, measuring fluxes of solar plasma, charting field geometries, calibrating timing. The larger installation, SWAN R2, arrives as the factory floor, deploying what appears to us as vast tails of dust and ionized gas, but which could in fact be engineered funnels, magnetic siphons designed to collect and process particles pouring outward from the Sunday. What astronomers interpret as passive cometary outgassing might, under this lens, be camouflage for the controlled operation of plasma engines tuned to harvest stellar wind. The physics of such operations strain human comprehension, but not imagination. Advanced civilizations might long ago have learned to work with nature rather than against it, guiding solar fields, accelerating ions, channeling exhaust flows, all while leaving signatures that blend seamlessly with what we call normal cometary behavior. We might be watching optimized machines masquerading as chaos. Consider more exotic possibilities. Near the Sun, magnetic field strengths soar, plasma densities throb, and relativity itself comes close to the surface. In such extreme conditions, micro-wormholes, tiny bridges across space-time, might be stabilized long enough to allow matter or data to pass instantly across interstellar distances. Our visitors might not be carrying resources away at all. They could be exporting them in real time, through conduits that wink in and out of existence with each cycle of solar rotation. The rhythms of the harvest would follow the rhythms of the star. Our Sun's 27-day spin churns its magnetic fields like gears in a colossal machine. Advanced harvesters could ride these cycles, extracting material during favorable alignments, pumping plasma in pulses we mistake for natural brightness variations. October 2025 may simply mark the next appointment in a timetable that has repeated for ages, invisible until now. The prize may not be ordinary plasma at all. Helium-3, scattered thinly in the solar wind, has long been imagined as the fuel for human fusion reactors. To us, it exists in frustrating trace quantities. To them, with sufficient technology, it may be harvestable in bulk. Or perhaps the goal lies deeper: exotic matter states born only in stellar chromospheres, quark, gluon plasma, magnetic monopoles, or other forms of matter that remain theoretical to our physics, but practical to theirs. The logic parallels our own history. Humans once followed seasonal herds, migrated to fertile valleys, and built cities near coal seams and oil fields. We dig where the resources lie. Why should cosmic civilizations behave differently? Their nomadic routes would not trace rivers or forests, but stars, flares of power scattered across the galaxy, each one a pit stop on a circuit of resource extraction. The soundscape of such harvesting, though inaudible in vacuum, might echo in other frequencies. Slow pulses in radio bands, bursts of static as magnetic field lines snap and reconnect, low-frequency hums woven into the electromagnetic background. To civilizations tuned to read them, these would be as obvious as the thunder of drills in a mine. To us, they are indistinguishable from natural noise. Station keeping would be the final challenge, for no body can linger near the Sun without resisting its gravity and chaotic magnetism. Any genuine harvesting system would require continuous control position adjustments, so subtle we would miss them, corrections buried in what we call outgassing jets. To our eyes, a comet brightens, shifts, flickers. To theirs, the machine holds its station, siphons its fuel, and completes its task. If the harvest hypothesis holds, then October 2025 is not a coincidence of comets. It is a scheduled operation, unfolding on a scale our ancestors could no more imagine than Stone Age hunters could predict the hum of oil refineries. Two visitors at once, one scout and one collector, converging on the Sun not to dazzle us, but to draw from a furnace whose power dwarfs every civilization that has ever existed on Earth. The requirements of stellar harvesting would not be subtle. Maintaining position near the Sun, drawing plasma into controlled channels, or stabilizing exotic physics phenomena would all create measurable signatures, non-Keplerian orbits, tail geometries that resist solar wind dynamics, acceleration vectors unaccounted for by sublimation alone, rotational shifts inconsistent with outgassing torques. These are the fingerprints our instruments are trained to seek, and so far, they are absent. Both 3I Atlas and SWAN R2 move as comets should, bound by gravity, illuminated by sublimation, behaving within the margins of natural physics. Yet absence of evidence is not always evidence of absence. Our telescopes can only measure what falls above their thresholds. Subtle manipulations of local magnetic fields, fine-tuned orientation control, or station-keeping protocols that operate by enhancing natural processes rather than violating them, might all leave signatures so delicate they slip beneath current detection limits. What appears as dust jets and ion tails might, in another interpretation, represent carefully executed industrial choreography, invisible to us only because we do not yet know how to read the script. The ethical dimensions stretch far beyond the physics. If stellar resource extraction occurs on a galactic scale, who owns the stars? Does our presence in orbit around this sun confer any form of claim, or would advanced civilizations regard us as irrelevant biological ephemera clinging to a fuel depot? Would we be tolerated as tenants, contested as competitors, or ignored altogether as ants at the edge of a refinery? The very framing of these questions exposes how unprepared our philosophical frameworks are for cosmic economics. Translating real comet behavior into imagined harvesting signatures highlights the challenge. Natural ion tails always stream away from the sun, their geometry dictated by radiation pressure and solar wind. Our observations of both 3I, Atlas and SWAN R2 conform perfectly to these expectations. No anomalous orientations, no persistent deviations, no controlled field structures beyond the physics of plasma and sunlight. Spectroscopy reveals familiar molecules, diatomic carbon, cyanogen, carbon dioxide, emitting at expected wavelengths. No unknown elements, no engineered isotopic ratios, no spectral fingerprints that demand artifice. Tracking data confirm Keplerian paths. The objects accelerate and decelerate under the sun's gravity exactly as celestial mechanics predicts. No course corrections, no station keeping, no indications of propulsion. If harvesting systems are present, they operate so deeply within natural behavior that they evade every diagnostic humanity has deployed. And yet the harvest scenario endures in imagination because it transforms chaos into commerce, coincidence into choreography. It suggests that our sun is not only the furnace of life, but also a pit stop in a galactic resource grid, a node in economic networks that stretch across stellar systems. October 2025 becomes not a random overlap of two comets, but a scheduled extraction window, with a scout and a collector docking invisibly at a fuel station that has operated for eons. If the sun is part of such a network, the deeper question emerges: how many routes dock here regularly, invisible to our untrained instruments? What cargo has been siphoned away into the dark, carried through wormholes or plasma conduits to civilizations we cannot yet imagine? The answers may already be encoded in the fire of the corona, written in patterns of light and plasma, too subtle for our current eyes, but perfectly legible to intelligence evolved or engineered on timescales we have yet to comprehend. Behind the blinding veil of the sun, in a region of sky where no earthly telescope can follow, October 2025 may stage the final act of a drama that has been building since two strange wanderers entered our system. In this concealed theater, where plasma and light erase our vision, speculation writes the script. The question is not whether something will happen. We know both 3I Atlas and SWAN R2 are on trajectories that bring them dangerously close to the sun, but whether what happens is natural physics or the culmination of a coordinated operation. Three scenarios, born of imagination yet anchored in the tantalizing anomalies we have observed, cast the visitors as more than passive wanderers. In these speculative frameworks, they become actors in a larger struggle for survival, information, or concealment. The first is the rescue scenario. In this story, 3I, Atlas is not a healthy scout, but a wounded machine. Its strange nickel emissions without corresponding iron, its puzzling chemistry, are not exotic fingerprints of alien formation, but the leakage of failing systems, a hull breach, a structural wound, a breakdown in its industrial skeleton. The interstellar visitor limps into our system, damaged and exposed, sending distress signals across the void. SWAN R2 arrives as the emergency response, a massive stabilizer disguised as a comet. Its brilliant tail, stretching like a banner across the October skies, conceals the unfurling of magnetic nets, energy stabilizers, and recovery equipment. To our instruments, These maneuvers look like natural cometary outgassing, yet in this scenario they mask the careful choreography of a rescue attempt timed to perfection. SWAN R2 intercepts 3I Atlas during perihelion stress, shielding it from the sun's fury, transferring power, data, or even life support for passengers who survived years of interstellar exile, only to falter at the final threshold. The second is the retrieval scenario, colder in its logic but no less compelling. Here, 3I Atlas was never meant to survive beyond its mission. It is a reconnaissance probe, designed to enter our solar system, observe, measure, and record, then signal for collection. SWAN R2 is the collector, the courier, large enough to carry data vaults and technological remnants back to their point of origin. The collision or fragmentation event that astronomers might record during solar conjunction is not destruction at all, but ingestion. The smaller craft is folded into the larger, its mission concluded, its data recovered. In this framework, the timing of October is not coincidence but logistics. Both objects converge when Earth's telescopes are blinded, ensuring the recovery operation unfolds without human witnesses. The economics of interstellar exploration make sense of this design. Disposable scouts can be seeded across star systems at relatively low cost, while collectors arrive at scheduled intervals to sweep them up, reducing the staggering energy demands of two-way interstellar travel. To us, the drama looks like comets brightening, fading, and perhaps breaking apart. To them, it is the closing of a reconnaissance cycle. The third is the most unsettling, the purge scenario. In this interpretation, SWAN R2 arrives not as savior or courier, but as executioner. 3I Atlas, whether probe or beacon, has revealed too much. Its strange chemistry, its anomalous behavior, may already have betrayed artificial origins. Worse, perhaps it has transmitted its intelligence back to its controllers, completing its mission and becoming a liability. SWAN R2 appears to erase it. The purge operation requires both precision and theater. The smaller object is dismantled, its fragments dispersed into the solar wind, its traces hidden in dust and plasma. What remains will appear, to our instruments, as natural disintegration under solar stress. But in this scenario, the spectacle is cover for an erasure designed to leave no forensic evidence behind, no proof that an artificial system once passed through our skies. Humanity, standing at the threshold of discovery, is denied the revelation. The evidence is destroyed before we can confirm it. In all three interpretations, the same physical facts are recast into radically different roles. Rescue, retrieval, purge. The choreography remains invisible to our blinded telescopes, hidden in the glare of the Sunday October, may pass with nothing more than the ordinary physics of cometary disintegration. Or it may mark the conclusion of a narrative we were never meant to witness, written not in human history but in the industrial strategies of civilizations that measure time in millennia. Advanced disintegration technologies, if they exist, might reduce a probe to its constituent atoms, scattering them so thoroughly into the solar wind that no trace of their artificial origin survives. The timing of such a sanitization would not be random, but calculated with precision, designed to coincide with the moment when human vision falters, when both visitors vanish into the sun's glare and Earth's instruments go blind. By orchestrating this hypothetical purge during the blackout, the supposed cleanup crew ensures that no telescope, no spectrograph, no digital eye will record the act of erasure. In these speculative frameworks, the luminous displays we admire from Earth, the brilliant tails, the swelling comae, become camouflage for operations operating at the razor edge of physics and engineering. What we interpret as volatile ices sublimating in sunlight could just as easily, in imagination, be energy weapons firing, disintegration systems humming, or propulsion technologies sculpting solar wind and magnetic fields into tools of deliberate design. The spectacle remains the same, only the narrative changes. Yet against these cinematic interpretations stands the unyielding voice of observation. Every telescope, from Hubble to Webb, to the amateur refractor in a backyard reports the same. Both objects move precisely where gravity dictates they should. Their brightness curves, their spectral fingerprints, align with the processes of natural ice sublimation and dust release. No sudden accelerations betray evasive maneuvers. No electromagnetic emissions hint at power grids or communication arrays. They are, as far as our instruments can tell, comets. Exotic perhaps, but still natural. Mars alone provides us with an alternate vantage point. On October 3rd, 2025, 3I Atlas will sweep past the red planet, close enough for its robotic sentinels, Mars Express, Trace Gas Orbiter, Mars Reconnaissance Orbiter, to turn their eyes outward. These spacecraft were designed for planetary science, not for monitoring interstellar enigmas, yet they may become our only witnesses to what unfolds during the blackout. Their spectrometers and cameras might catch a flicker, a plume, a disruption inconsistent with natural cometary physics, or they might see nothing at all, confirming only what Earth-based telescopes have already concluded. But even these Martian observers labor under limitations. The distances are vast, their instruments optimized for Martian weather and geology, not deep space reconnaissance. Only the most dramatic deviations, an unexpected outburst, a visible fragmentation, a sudden alteration of trajectory would rise above the noise of data. Communication delays compound the problem. Signals between Earth and Mars take anywhere from 12 to 24 minutes to cross the void, ensuring that whatever drama plays out near the Sun will be over long before human hands could respond. We are spectators only, never participants. The allure of these conflict scenarios lies less in evidence than in psychology. Human beings are narrative creatures. We take ambiguous events and clothe them in familiar patterns of struggle, rescue, destruction, and resolution. A clash between two cosmic visitors satisfies that deep narrative hunger, transforming random physics into purposeful action, even when that purpose involves annihilation rather than creation. When the glare finally fades and our telescopes recover their quarry, the reckoning will come. Will two wanderers re-emerge, unchanged, their orbits and compositions matching the predictions of cometary models? Or will one vanish, its absence demanding explanations beyond the quiet mechanisms of ice and dust? If so, we may have to accept that the universe contains conflicts playing out in silence, battles waged in the plasma of stars, invisible to us until their echoes alter the number of lights in our sky. One by one, the instruments fall mute, as both travelers slip into the blinding theater of the Sunday. Observatory feeds flicker into static, coronagraphs saturate under hydrogen fire, and the grandest performance in our cosmic neighborhood vanishes behind a curtain of incandescent light. What remains is absence, memory, speculation, and the relentless tick of atomic clocks counting down toward revelation. In university domes and government facilities across the world, astronomers hold their collective breath. Social media becomes a hive of sketches, theories, and impromptu prophecies. In this forced quiet, imagination rushes to fill the void where data should be. Every scenario takes on equal weight, from the plausible to the fantastical. The mind's eye conjures frames of an unfinished film, one object returning altered in color or brightness, scarred but transformed, the other diminished, perhaps extinguished altogether, consumed by forces invisible to us. Or perhaps coronagraphs will reveal a halo of shattered fragments, where once there was a solitary traveler, a silent record of a cosmic transaction performed in secrecy. And then again, perhaps nothing at all will change, save for our own appetite for meaning, our hunger to find stories within the machinery of ice, dust, and gravity. The path of reality runs through patience, through the discipline of observation. SWAN R2 will reach its most public splendor in late September and October, its tail sweeping like a brushstroke across the evening skies, a spectacle for amateurs and seasoned observers alike. 3I Atlas, by contrast, will remain hidden until December, when it emerges from solar conjunction and professional instruments can resume their careful catalogues of spectral lines and orbital refinements. The evidence to this point points clearly to nature's handiwork. Two extraordinary comets whose convergence is explained not by intention but by mathematics, not by design but by the probabilities of orbital mechanics. Yet the true richness of these encounters lies not only in confirming natural explanations, but in the knowledge they carry. Each observation sharpens our understanding of how other star systems form, how pristine material from the outer galaxy evolves, and how ice and dust respond when thrust into the furnace of our Sunday. Still, between observation and interpretation, in the silence between the data points, stories take root. We are creatures tuned to pattern, haunted by questions of intelligence and purpose in a universe vast enough to hold both mundane physics and extraordinary possibility. The October silence becomes a canvas for projection. If an ancient machine kept an appointment with our star, what would it see here? A young world alive with a noisy species, broadcasting its chatter across the electromagnetic spectrum, daring to lift its eyes and wonder if the visitors meant more than they seemed. Would such a machine find what it sought, or would it discover something altogether unexpected, an intelligence still uncertain of itself, but hungry for meaning, hope, and permanence in the face of cosmic time? December will bring answers. When the visitors re-emerge from the sun's glare, the instruments will whisper again of positions, of velocities, of spectral fingerprints, and the great question that has threaded through these 14 chapters will demand an answer: comet, fortress, or reply. Until then, we wait. We wait in the hush of October, held in the sun's gravitational embrace, listening for stories the universe may be writing in a language we do not yet know how to read. The cosmos keeps its secrets well, but for those who endure, patience is always rewarded with revelation.